All right, 11.5, volumes of pyramid to come. Okay. This is a direct link to what we did yesterday. It's not very difficult if you understood yesterday's stuff. Yesterday's formula, volume equals capital B times H, right? Capital B times H. Today's formula is the exact same thing, but we multiply by 1/3 first. Okay? And the reason for that is that every pyramid that we ever come across, okay, is coming from some prism. Okay? Every pyramid is, if I start with a prism, I should be able to carve away some of the corners of that prism and eventually develop a pyramid. Does that make sense? Look at those three pictures on the bottom. Start with those prisms, carve away, and eventually you have the pyramid, right? Okay. If the prism and the pyramid have the same base and they have the same height, okay, then the pyramid is always going to be 1/3 the volume of the prism. Okay. If we have a little bit of time later on in the week, maybe we'll go through and derive that formula, show you where the 1/3 comes from. Okay. But it's that relationship that the pyramid is 1/3 of the prism. Is that okay with everybody? If we go through and find all those volumes, respectively, of the prisms and respectively of the pyramid down at the bottom, you can see in that first one, pyramid volume is 1/3, prism volume is 1. In the middle one, prism volume is 1 times 1 times 3, which is 3. Pyramid volume is 1. Is there a 1 to 3 relationship there between those two? And then the last one on the right, okay, the prism volume would be 2 times 2 times 3, which is 12. The pyramid volume is 4. Well, 12 divided by 4 is 3, right? Okay. If you had these shapes separate, okay, the idea is if I take that purple pyramid, fill it up with water, pour that water into that prism that is stuck to the purple pyramid, I would need 3 of those purple pyramids full of water to fill up that one prism. Does that make sense? Okay. So that 3-to-1 relationship is always true, and it's going to be a test question on Tuesday. Okay? 3-to-1 relationship. A lot of times, okay, this picture up there and then all those pictures, one half AP is going to work, but be cautious about that, be smart about that. If your base is a square, don't use that, use S squared. If your base is a triangle, use 1/2 DH. But if it's a hexagon, pentagon, octagon, use 1/2 AP for your capital B. Okay? Couple things as we go through. We'll do a couple examples of this. But it is very similar to what we did yesterday. If you can find what your base is, find what your base is. The tablet died, so give me 1 second. There we go. All right, so volume of a pyramid is 1/3 capital B times H. Okay? B is going to be this shape down here, right? It's your square. So how do I find that area? All right, so B is going to be 40 squared, which is 1,600, right?
Yes, sir.
I got to find H, which is that distance there.
Yep.
What would that one be? 20. Okay? So Pythagorean theorem says H squared is equal to 25 squared minus 20 squared. Okay, so that's 225. I'll square root it. Chuck says that's 15. So now plugging in, I have 1/3. B is 1,600. H is 15, right? Of those three numbers, which two work together real well? 15 and 1/3. 15 times 1/3 gives me 5. Okay. What's 5 times 16? 80. 80. Okay. And then, okay, so what Chuck is saying is 5 and 16 give me 80, but this is a factor of 100 in there, right? So he says 80 hundreds. 80 hundreds is 8,000, isn't it? Okay? And that would be feet cubed. Feet cubed. And there's my volume of that pyramid. Okay? Is that much different than yesterday? No. Okay? You got that 1/3 out front. Okay? A lot of times, people are going to make the argument that volume is easier than surface area. Would you guys agree with that? Okay. When we get down to a question that deals with cones, okay? Pyramids, through what we've been talking the last couple of days, are going to evolve into cones, right? So the formula should be the same, okay? The volume of a cone is 1/3 BH, okay? 1/3 BH. But B for a cone is always a base. Circle, okay? So I have 1/3 pi r squared h as the more specific formula, okay? Again, what that means to us is if I have a cylinder, okay, and then I have a cone that is on the same base and the same height as the cylinder, it's going to take 3 of those cones full of whatever to fill up the cylinder. Water, whatever. It's like the green that picture up there. Corn. Okay? So, 1/3 pi r squared h is the formula for finding the volume of a cone. That's the same as the volume of a cylinder, except for you multiply it by 1/3. So here, we got a question. Okay? Now this is a ridiculous answer here in a little bit. Okay? But I want to go through and talk about how we can use volumes to determine a time. Okay? There is a conical reservoir, and we're putting water in at 2.3 cubic centimeters per minute. Okay? Now what that means is 2.3 milliliters per minute. It's a very, very small amount of liquid for every 1 minute. So it's just a drip. Does that make sense? Okay. Now we want to fill this thing up. This reservoir is pretty large. Okay. It's got a 12-meter radius. Okay. And it's got a 30-meter slant height. Okay. So it's a pretty large cone. I want to fill it up. So let's talk about the volume of that thing. Volume is going to be 1/3 pi r squared h. Okay? 1/3 pi is constant. What is r going to be in this case? 1200. Okay? And I think it's a good idea to leave it as 1200 because it's going to be centimeters squared, right? So my units are centimeters. And that makes sense for the conversion that we're going to have to do here in a moment to get into minutes, because that conversion factor refers to centimeters cubed, doesn't it? So now we got to find out what h is, so we got to do the Pythagorean theorem. Okay? So when I do the Pythagorean theorem, okay, this is 1200, right? Yeah. What is this? 30. No. 3,000. 3,000. Why? Okay, so that one's in meters. We got to change to centimeters. Some people, like I said, some people say, well, why did you change that one to centimeters? Why not change that one to meters? I could do that. I could change it to 24 meters. But then my volume is going to be in cubic meters, which does not align itself real well to deal with this conversion rate because of that being cubic centimeters. Does that make sense? It's doable, but it's probably going to be a little bit more work in regards to conversion. Okay? If I go through the Pythagorean theorem, it's going to be it's going to be, let me get my calculator up here. All right, it's going to be 3,000 squared. Okay, minus then
1200 squared. Bear with me while this thing. All right, so we're going to take 3,000 squared, subtract from it 12,000 squared, and then take the square root of that. So it ends up giving me this distance here, using the Pythagorean theorem, gives me h to be 2749.55. Okay? I should then be able to run this through and find a volume of this cone. Does that make sense? So I'm going to run that through my calculator real quick. So 1/3 pi times 1200 squared. All right, so when I run that through, the volume turns into being this number: 414,621,6808, and that's cubic centimeters. That's pretty large. Okay, that is 4 billion cubic centimeters. Okay. Now I want to change this to a time. So I need the cubic centimeters to disappear. So I need centimeters cubed down here, right? And I need minutes up here. And this is why I wanted to show this question, because yesterday with the conversion rate, all we did was multiply, right? And people get in the habit of seeing whatever my conversion rate is, I always got to multiply by it. Well, you might have to multiply by its reciprocal, which is the same as doing what, Carter? Dividing. Okay? So when I put that 2.3 in here to get these to cancel, we find out that we're actually dividing instead of multiplying. And that's something to pay attention to. I always get the question, well, how do I know to divide or multiply? It's by setting that up, by getting your units to cancel out. It tells you whether you divide by that conversion rate or you multiply by it. Okay? So when I take that number and divide by 2.3, okay, I get 1802702,960 minutes. Okay? Okay? So that's in minutes. So that's 1.8 billion minutes. Okay? Now that's a lot. No, I'm the only one in here that's been alive for 1 billion seconds. Okay? So let's kind of divide this out and see how I change that into hours. How do I change that into hours? No, divide it by 12. 24. Okay, we'll divide it by 4. Oh, that'd be days. Yeah, you divide by 60. Okay. 60 minutes for 1 hour, right? So that's why I'm going to divide by 60. So we divide that by 60. It gives me... So I divide it by 60, and it gives me these hours, so it's like 3004504.933 hours. I want to divide that by what to get in the days? 24. Okay. What if now I've got a number that's 1251877, and that's in days. How do I put that into years? 360. 365. Okay. So it gives me 3,429.8 years. 3,429.8 years. So it's going to take a long time to fill up this reservoir, right? And the reason is we have just a trickle out of the faucet. A pretty large volume, probably a third of the size of this room. Okay. Maybe a little bit bigger than that. Probably a little bit taller than that. Okay. Because it's about 27, so it's about, kind of visualize this. This room's probably got a height of 12 feet. Okay. The height of that cone is 27 meters. Okay. So you start to see, maybe kind of visually how big this cone would be. It's a couple stories tall. And it's about the width of this room in regards to its ratings. Okay. So it's a big, big cone. And it's being filled up by just a drip out of the faucet. It's going to take a long time to do that.
I just chose random numbers here, okay? That's why they worked out to be such a large result. But you can see how we can use flow rates, okay, 2.3 cubic centimeters per minute to develop a time to fill something up. Volumes are allowing us to do that. That make sense? We do these types of questions. All right. So your homework, there's a math Excel assignment. There is that